Thank you very much for the introduction and the invitation. And I want to thank Sebastian for two things. One is for making me like those kind of things. I think without Sebastian I would never be interested in machine learning. And second, for giving such a great first half of the talk and basically putting me in a situation where all I have to do is just start from this theorem. So let me just remind you really quickly what we still have to do. So we basically got the balancing between exploration and exploitation done. So our algorithm kind of throws a coin and decides whether to exploit or to explore. We already know how to exploit. We just take the point with the smallest expectation. So what's left is to find an efficient way to explore, which means we want to find a way where we'll actually learn something about where the actual minimum of the loss function is. So this is exactly this theorem, and I think you can think about it as some sort of a hide-and-seek theorem. So why hide-and-seek? So you have basically your function f, which, as you remember, was the expected loss conditioned on everything we know so far. So we don't know what the actual loss strategy or the loss function of the adversary is, but the expectation is encoded in this function f. And then the adversary really kind of wants to hide from us. The adversary really puts the minimum at some point z. Okay? And we know that the minimum of the loss function of the adversary, which we call g here, will be smaller. So if this minimum is 0, the minimum of g will be smaller than minus epsilon. And what the adversary wants to do, he wants to hide from us in the sense that he wants this function g to differ from f at as few points in space as possible. So he kind of wants the function g to collide with f as faster as possible. So he wants to hide the difference between g and f. And what we want to do is we want to, well, seek him. And we do that by finding this mu, which we can think about as an exploratory measure for f. So mu is the most efficient way to seek where the adversary is hiding. So we want to somehow find a measure such that for any such g, we will actually have a good probability to see a difference. Okay, this is basically the thing we're left with. And even if you didn't follow all the details in the first hour, I guess it kind of makes sense that this is the thing we need to do efficient exploration of basically what the adversary's function is. Okay? Any questions before I start? So, good. So, first few minutes I want to dedicate to this pretty simple case, which can be seen almost as an exercise, just the one-dimensional case. Okay? So the first observation I want to have is the following. So if this is the function f, suppose I know where the point z is. Of course I don't, but suppose that I did know, then so if we know what z is, what we can do is just take the uniform measure on the interval between the minimum of F and Z. And this will do the job. So this is F, this is Z. And for intuition, it's kind of, it makes sense to think that once we know where Z is, the only thing we know about G is that it passes through the point Zn minus epsilon as a point in the graph in R2. What the adversary wants to do is he wants to collide with F as quickly as possible. Right? The adversary has no interest to do something like, okay, at least when we go right here, I guess, the adversary wants to collide with F as soon as possible, and once he did, there is no point in separating from F, because he wants to hide, right? So, if this is argument of F, and this is Z, which we can think about as argument of G. If I take a uniform measure in this interval, this should do the job. And the reason is the following. So first, let's observe that, well, nothing really happens if I rescale space so that this distance is 1. So the size of this interval, we can think about it as 1. If we rescale space, we don't change the y values, right? We don't really change the fact also that the functions are Lipschitz because, well, I guess, okay. One thing I didn't write here is that the diameter of the domain has to be bounded. So the diameter of K is 1. So when we rescale, we really just inflate things. And then the easy observation is that if you look at G, it's going to meet F at some point, which we can call x naught. Now, since G passes through minus epsilon, the derivative at x naught has to be at least of order epsilon, right? Because this distance is less than 1, and F is positive. This means that if I look at the difference around the point where they collide, this difference, I can actually compare it to this distance up to a factor epsilon. So for all x, we have something like f of x minus g of x is at least epsilon times f of x naught minus g of x naught. Sorry. It's at least epsilon times x minus x naught. This is what I wanted to say. So the distance in the y is at least epsilon times the distance in the x, again, because the derivative of g is at least epsilon. And since we took the uniform measure over this interval, we have many points for which this distance is order 1.
For x on the left.
Yes, for x on the left, that's a good point. It could be that they meet very close to this point, and then actually all of this interval is okay. Because f is positive and g is, it's less than the linear. Okay, so if they meet close to this point or at this point, then our situation is actually better because f is positive and g is below the linear function connecting minus epsilon to 0. Okay, so, right. This was actually the second case. And, okay, you agree that once we know that, then if we take mu to be uniform, then many of the a typical point will have that this distance is constant, which means that f of x minus g of x is at least constant times epsilon. And we're done. Okay, so this is fine as long as we know where z is, which of course we don't. And if we think about it for a minute, we couldn't just, for example, take the uniform measure over all of k, and the reason is that the adversary can always hide very close to the minimum of f. It could be that the distance between z and the minimum of f is very small, and then I really have to explore. Basically, it's clear that I somehow have to explore this interval. So what's the solution to this? Well, actually, I don't really have to know where z is. I just have to kind of know more or less what the distance between z and the minimum of f is. If I know it up to a multiplicative factor of 10, I'm also fine, right? It's still okay if I put a uniform point between here and 10 times this interval. And this motivates us to do some kind of multi-scale construction of this thing. So basically what we'll do is we'll guess how far z and the minimum of f is in terms of scale. We'll guess every scale between epsilon and 1 in multiples of 2. And then we'll basically take a measure which first chooses the scale and then chooses the uniform point here, right? What we'll get is that, well, that just the number of scales, it's not hard to see that the smallest scale we have to look at is something like epsilon because of the Lipschitzness. And, well, we'll just lose log epsilon, but up to that we'll be fine. So really, our construction is mu will be the sum over all k between 1 and log epsilon. And here I'll just take the uniform measure between minus 2 to the minus k and 2 to the minus k. So this is not a probability measure, but if I divide by log epsilon, then we're fine. Okay, so this finishes the one-dimensional case. It already shows us that, well, we definitely need some kind of multi-scale thing to do.
Epsilon is more than 1 or bigger?
Epsilon is, well, epsilon should be thought of as much smaller than 1.
So it's
well, let's assume that it's actually smaller than 1. It doesn't, if it's bigger than 1, it only helps us.
Just log 1 of epsilon.
It's, or absolute value of log epsilon. Yes, that's log 1 of epsilon. Okay. So that's one dimension. And now let's try to understand where the difficulties arise when we think about the higher dimensional case. So I want to consider a few examples. And the first example I want to look at is just f of x equal to norm of x squared. So f is just a parabola in high dimensions. And the z's I want to consider are just, well, I want to consider all the z's which are, so let's say this, okay, this is the origin. I want to consider all the z's in the unit sphere. So all the z's which are at distance 1 from 0. And, well, if you think about it, we can build a function g which passes through the points z and minus epsilon. So this is now in a higher dimension. And we can make the function collide with f everywhere, but, well, in one dimension we can make it collide with f everywhere, but on a set looking like this. In higher dimension, if we look at things from above, so this is the origin, this is where f is 0, we can make g collide with f everywhere, but on a set probably looking something like this. So if we look at this set where f and g differ from above, when we go into or outside of the blackboard, we can make g go like this and collide with f as fast as possible. And we can make the set where they differ to look something like this. And at this point, I want to answer the question about Thompson sampling. So, if the points, the minimum points that the adversary chooses are uniformly distributed on this sphere, then, well, I'll have one of the rotations of this set. But the point is, if you just take a uniform point of this on the sphere, your chances to hit one specific set like this are exponentially small in the dimension. Okay, in other words, what I'm saying is the measure of the intersection of this set with the unit sphere is exponentially smaller than the measure of the unit sphere. I mean, by an exponential factor in the dimension. So if you really try to just do Thompson sampling, you'll never find the adversary. I mean, okay, up to an exponential in the dimension factor. Okay? So, good. So this kind of already tells us that it doesn't make much sense to look for the adversary at the scale of z. You see, I mean, if I only pick points whose distance from the origin is this, in this case 1, I'll always get an exponential penalty. But where can I actually know that I'll find the adversary? So if I go close to the origin, if I go here, then, I mean, this is something one should write down and see, but the set where the two functions differ, when it gets to the origin, it's actually tangent to the origin. So very close to the origin, this actually looks like a half space. Only far from the origin, it looks more like a cone. So if I look close to the origin, I have a much bigger probability to actually know which direction z is pointed. Okay, so this already gives us some intuition that says basically, okay, probably you need to explore near the minimum of f. This is where the two are probably going to differ. Any questions so far? Okay, so this is the second example I wanted to show. And does this example make it clear why Thompson sampling is not going to give polygon? Good. The third example I want to give is basically two-dimensional. Let's look at the function f of x is equal to x1 squared. So this is just the first coordinate, and we're in R2. So the graph of f looks something like that. G differs from F by epsilon somewhere, and what I want to say is that if I look at this line, so just the bottom of this thing, and if I put my point Z exactly under this line, so this is Zn minus epsilon, then I guess it's not so hard to imagine that I can connect G to F basically everywhere except on a set which is very close to this strip. So we should imagine epsilon as being a very, very small number. F looks like this. G is just below. And since it's really like closely below, when we go in these directions, we can quite quickly connect to F. So the adversary really can pretty easily hide in a strip. Well, basically in the strip defined like this. x1 is less than, if you calculate it, it's something like root epsilon. Okay, so this is a very small strip in 2 dimensions, and the point that this example is showing us is that, well, in this strip I can just think that everything is one-dimensional, but I definitely have to understand that F looks like this, and my measure mu must give a substantial weight to this strip, even though the Lebesgue measure of this strip is very small. It's a function of epsilon. So we need to have that mu of this thing is big. So here we have a multi-scale thing, but the multi-scale, this already suggests that we have to also pick the directions wisely. Okay, something maybe according to the Hessian of f at 0, or something like that, I guess. Okay. Even though the Hessian of f at 0 is not enough, but I guess this suggests that, you know, this is the spirit of the thing. And of course, I can generalize this example to something like this. In higher dimension, I can think of f of x as being, okay, let me write it again. F of x is the sum over coordinates I, xi squared, normalized by 2 to the minus I, or something like that. So every direction the curvature will be on a different scale, and, well, probably I'll have strips like that in many directions on different widths, and we'll need to somehow, you know, spread our measure mu to take care of all of them, but each one of them is kind of at a different scale. Okay, so these are the examples I wanted to show to kind of see where the difficulties lie, and from now on let's talk about the actual proof. Any questions so far? Okay. So, here's the first idea of the proof. So, which I guess we can call line of sight. I want to go back to this example, and let's suppose that I take the measure mu to be a measure which is, well, how do I draw it? Okay, I'll try to draw it here. Let's take this surface and draw a little circle on this surface. So on the side of this surface, let's go down from this circle and take the corresponding domain in R2. So the domain where if you take f of this domain, it goes up here to somewhere on the side of this parabola. And suppose I take mu to be the uniform measure on this thing. And I want to ask which functions g, or basically which points z that for which g is small will be exposed, will be basically found by this measure mu. And what I claim is that this measure mu will take care of all the points z that have an open line of sight to this portion of the graph of f. So I have the graph of f, I have some point on the graph of f. Think of this graph as embedded in R3. Some points don't have a line of sight to this point. For example, if the adversary hides here behind the surface, then this point is hidden from that point. On the other hand, if the adversary is on this side of the surface, so this thing is really looking this way, and if I take a point z and minus epsilon, which has an open line of sight to this thing, it's not blocked by basically the other part of the surface, then the adversary cannot hide here. Meaning, if there is an open line of sight, then any convex function passing through this point will have to differ from f on many of the points of this thing. And what is the reason to this? The reason is basically almost one-dimensional. So I guess while you're trying to figure out the reason, let me try to write this a bit more formally. Okay? So suppose that we have 2 points. Let's call this point x and w are such that we have the following thing. So I guess maybe let me do 2 definitions. So Bxr is the ball centered at x with radius r, and mu sub b is uniform, is just the uniform measure on b. So suppose the points are such that if I take the uniform measure on a ball centered at x and has radius delta, which we'll soon say what it is. It's some 1 over some poly n, such that if I take hold on, yes, I want to say, okay. So I take the gradient of f inverse at the point applied to a ball centered at w with radius delta. Okay, let me change this a little bit. With with radius delta times the norm of W. We'll soon see what this means exactly. Then this measure is at least 1/2, meaning that above this point, most of the gradients of f are pointing kind of in the same direction. Yes?
So you assume that f is differentiable?
Yes. I mean, it can always be modified slightly to be smooth. Yes. So we can assume this. Good question. Okay.
It's 1 inches, so it's differentiable and multiple. F is 1 inches, no, in your assumption.
Yeah, it's also convex. Yeah. But I mean, changing f slightly on the scale of less than epsilon is always okay. So, assume it's this. So suppose we have this, and then for all z, this is my point z, such that there is a line of sight between this thing and z, which in other words means that ZW, which is really the gradient of f, is at least the norm of the gradient times some constant, let's say over 10 here. And for all g with g at point z is less than minus epsilon, we have that this measure well, this measure discovers g in the sense that maybe I'll write this here. So we have that this measure gives this set. This is already so wide such that okay, so basically if I take a uniform point here, any function g which has a line of sight to this point, and the line of sight really means this, right? It really means that the gradient at that point has a positive correlation with the difference between z and x. I guess, okay, it'll make a bit more sense if I write here z minus x. But it doesn't actually matter so much. Okay? And why is that true? This is, I mean, in a sense, it's just back to the one-dimensional thing. Let's think of this point in this circle and just fix one fiber. So fix one line that passes through this point and cuts this circle. Okay? On this line, if we restrict the functions f and g to this line, what we see is that at this point g is equal to minus epsilon. At these points, f has the gradient pointing in a direction so that so just on the restriction on this line, we have the point z, we have the point x, and we know that g looks like that. And the point we know about f is that the gradient above this point is going this way. So this is f. And at this point, on this one-dimensional fiber, we can just invoke the previous one-dimensional argument. Right? What we needed about the gradient is just preventing the fact that the gradient of f here is going the other way. So maybe the minimum of f could have been here, and then this wouldn't be enough. But if the minimum of f is on the other side than the minimum of g, then they have to collide, this way. Okay? Good. So this idea, which is, well, it's basically a lemma, the way it's formulated here, basically tells us that we want to find a few balls which give us an open line of sight to all of the space. So we want every z to be in the line of sight of some ball. So here we just took one ball, b of x and delta. We want to take some union of balls which together kind of have a line of sight to everywhere. And then we'll be done. Okay?
Just maybe you should, I don't know if you said it that, you don't see this on every fiber. You see it on most fibers.
Yes, so, right. So, we know that the measure where the gradient is good is at least a half. It could be that on some fibers, right, thanks. So it could be that on some fibers the gradient is actually going in a bad direction. But at least we know that for most fibers this is true, and then we can do some forbidding, and everything will be fine. Okay. So we have this, idea. And this idea, I want to combine it with some lemma which we will just take as is, and this lemma is basically saying that for every ball of radius slightly bigger than delta, for every y, the ball centered at y of radius, let's say, n times delta. Delta is polynomially small in n. This is slightly less polynomially small in n. For every such ball, there exists a point x in this ball such that the pair of points x and w, for some w, satisfy star, where star is this. So what I want to say is the following. For every ball that I take, let's look at the surface of the function above this ball. So the gradients are pointing in many ways, in many directions. But there is some direction where, a good proportion of the gradients are not so far from this direction. So it can't be, it could be that the function is the gradient is turning as I vary my point in this ball. But, the Hessian of the function, all in all, is, the function is Lipschitz, it's bounded, so at least on average, the Hessian cannot be too big. Which means that I can probably find a small ball where the gradients are kind of concentrated. Okay? And the condition star exactly means that above this the ball centered at x, the gradients are not pointing very far from each other. They're kind of pointing at the same direction of space, which means that the points with line of sight will have a line of sight to all of this thing. Okay, so this is the lemma, and I mean, once we have this lemma, and we have another very simple observation that by the convexity of f, we always have that the gradient of f at the point x dot product with x minus x star, which we understand as argmin of f, so just the offset between x and the minimum, this is always non-negative. Right? If I go in some direction, then the gradient also is correlated with this direction. And why does this help me? It helps me because if this is f, and I look at some z, which is here, if I take a point x, which goes in the same direction as z, then the gradient of f at this point is positively correlated with z, right? Which means that I can take this ball, find inside it a smaller ball using this lemma that satisfies star. This smaller ball, we know that it will expose the adversary for every point z, which satisfies this gradient condition over there, which means that it will expose the adversary at some half space whose direction must be correlated with z. So in a sense, I can find a ball which exposes the adversary at some half space, which is correlated with every given z. And what we want to say is that I can take a union of some balls which basically exposes everything together. Okay? Please ask questions if you feel like I'm becoming vague, because I don't really have time to get technical, but I want to give you some ideas. So let me sum up what we know. So what we have so far. So for all z, there exists some ball b x delta such that mu sub b x delta exposes an adversary hiding at z. Well, this is not exactly correct because we have some kind of deficit here. We need the gradient not just to be correlated. It's not enough that it's bigger than 0, it actually has to be bigger than something slightly bigger than 0. Therefore, it doesn't really expose the adversary hiding at z. It exposes the adversary hiding at z prime for some z prime which is close to z. So let's just agree that every time I write delta, this is 1 over poly n. Okay? So I can't expose every point using some ball, but I can expose, a point close to every point. So if this is our space, then I know that every point z, there exists some half space which almost touches z. Which can be exposed if the adversary hides there. So this is z1, and if this is z2, then I maybe have this half space. And I can find basically a union of half spaces which almost covers my space. But some points can still hide. And if we remember that example that's curved only in one dimension, the points that will still be able to hide, the ones that for which there is no line of sight basically to almost any point on the surface, will be exactly the points under this line, if you just remember that example. Okay? And now we have basically two facts from convexity that will be useful to us. Both of them are basically application of the so-called one is the Carr-Theodori theorem and one is Helly's theorem, which are, I guess, well-known principles in convexity, and basically they're saying the following thing. If I can expose almost every point, if for every point I can expose something close to it, then the union of everything that I can expose is contained in a slab. So another way to say it is the following. If we have a subset of the set of all directions such that for every direction x, there exists some theta in the subset. So think about h as the subset of all such directions where I can expose. I mean, all the directions of these half spaces. Suppose that I know that for every x there is some direction which almost exposes it, meaning that x theta is almost positive, so it's bigger or equal to minus delta. Then we have two things. The first thing is that there exists a subset of H with cardinality at most the dimension plus 1 and with the same property, basically. So I can find a subset of directions which still expose almost everything, but it's just a union of a polynomial number of such balls. And 2, there exists some theta tilde such that all the non-exposed points are in a slab with direction theta tilde, such that every x for which x dot theta is smaller than 0 for all theta in this h prime, which is basically all the points which are not exposed by any of these half spaces, is inside the slab y such that y dot theta tilde is smaller than delta. So basically I can take care of everything but some small slab, which basically goes back to this example we had. F of x is just the first coordinate squared. Right? If I take the first coordinate square, and I can easily take two small balls which expose everything but whatever there is in the middle. You know, if it looks like this, then this slab will not be taken care of. Okay, so we can take care of almost the whole space. I mean, if we take the union of all these things, then in the end we know that the union contains everything but a slab like this. So what do we do at this point? At this point what we can do is just take this slab. We already got rid of everything. The adversary can't hide outside. So now we just rescale space. We inflate this slab. What it will do is it will basically change all the gradients going in this direction and make the gradients going in this direction bigger with respect to them. So if you think about this example, so I guess it'll be easier if we think about x1 squared plus epsilon times x2 squared. So we have a little bit of curvature in the other direction, but very small. What we'll do is we'll expose everything but the central slab, and we'll inflate. And then again we'll expose everything but the central slab, and we'll inflate again. And after we do this several times, then this curvature and this curvature will already be the same. And at this point, well, we'll just have to deal with the usual quadratic thing, usual isotropic thing, which can be dealt with by taking just a small ball around the origin or something like that. So basically the next idea is just to say, okay, just rescale and do the whole process again. And I guess the only thing that still needs to be done, which I guess I don't have any time to do, is just we need to claim that this process of rescaling at some point converges to something. I mean, we can keep rescaling, and in the end, what will we have? So here it's not so hard, I guess, to believe that if we keep rescaling our space in many different directions, there are two possible outcomes that can happen. Either we've rescaled enough times, either we rescale more or less in the same direction all the time. And then what we're left with is just essentially an n-1 dimensional setting. If you remember, the function was Lipschitz, so if we rescale the same direction, if we inflate the same direction enough, then, well, it becomes, it has a much better, much smaller gradient in this direction. which means we can just assume it's constant in that direction. And then we go to a basically codimensional one subspace, and we just continue our process there. So this is kind of an induction over the dimension. Either that, or we don't do it in the same direction, and well, the rescaling basically just focuses around the point. Maybe first we rescale this, and then we zoom to something like this, and we keep zooming in until we're just around one point, which is the minimum of f. But if we're around one point, then, again, since the function is Lipschitz, then f is essentially constant in a small enough neighborhood of the origin. Okay? And, okay, I guess, hopefully this gives you some idea of what's going on. I guess I'll stop here.
You use a geometric point of view to explain your theorem. Maybe it would be interesting to use a probabilistic point of view because you want to construct a measure mu for a function f.
Yes.
So on the class of function g, so that the measure of the points such as the
Yeah.
So this looks very much like the Levi-Prokhorov, Kantorovich, Wasserstein distance between some set of because when you have a mu of the x such that f of x satisfies something, you define a random variable f.
You mean you can just do duality, or
Yeah, because it looks like that you construct you want to.
Okay, I guess.
Yeah,
The point will be how to. I mean, if you can use some kind of Kantorovich duality to do that. I don't see it exactly, but I don't see where convexity can be used. Then.
The difference that in the classical transportation distance, you want to transport one measure to another. Here you want to transport one measure of the f to the class, to a convex class of g on the variable.
Okay, I guess I have to. We haven't thought about this direction.
And,
I'll be happy to fit it.
you could use because you obtain your equation on the gradient on the duality theory of you have this
Okay, I'll be happy to talk to you about it. I don't know. I mean, if there is a proof along these lines.
I don't know.